Hey, I'm the wannabe coder, and welcome back to the channel. This is episode 3, and in this video, we're going to add the player character and give them basic movement. We'll set up keyboard input so the player can move left and right, add a simple jump mechanic, and we'll keep everything clean by placing all the player logic inside its own file. Everything will be structured using classes, and by the end of this episode, you'll have a player on screen with basic movement, fully controlled using the keyboard. First, let's do a quick recap of where we're at. In the previous episode, we built the visible elements of the level. We drew the tower walls, stacked a list of randomly sized platforms, and connected everything to the game loop. Now it's time to make things interactive. Alright, let's open up constants.py and define the player's size, movement speed, and other parameters. Scroll down to the last parameter we defined, which is the player's pixel size, and let's add the next few lines. Player underscore shape underscore size equals player underscore pixel underscore size divided by 20. This converts the pixel size into the scale factor that Turtle uses for shape rendering. Next, we'll set the player's starting vertical position. Player underscore start underscore y equals ground underscore y plus open parenthesis. Plat underscore pixel underscore size plus player underscore pixel underscore size, close parenthesis divided by 2. This places the player's feet right on top of the floor platform. Remember, Turtle's coordinates refer to the center of each shape, so we take the floor's center position, add half the platform height to reach the top, then add half the player height so the character stands perfectly on the platform. Now let's define some basic physics parameters for movement. Let's start with the jump distance. Jump underscore distance equals 14. That controls how high the player jumps. Then we define the acceleration. Acceleration equals 0.5. That's how quickly the player gains speed while moving left or right, just like in the original Icy Tower. Next, the maximum speed. Max underscore speed equals 15. That's the fastest horizontal speed the player can reach. And finally, turn underscore factor equals 5. We'll use this to make mid-air turns feel smooth. So if the player is jumping right and switches to left, they'll curve naturally into the new direction, instead of snapping. These parameters can all be adjusted to fine-tune how the movement feels. Since Turtle Graphics behaves a bit differently across computers, if your player feels too slow, too fast, or not as smooth as what you see here, just tweak the values until it feels right. Now let's go to our main project folder and create a new file to contain all the player logic. We'll name it actors.py. Once you've created the file, go ahead and open it up. This is where we'll define the player class, along with all of its methods, for movement, physics, and collisions. At the top of the file, I've already added a helpful docstring. It explains that this module defines the main player in the game, that each actor is built on top of the Turtle class, and that it includes logic for positioning, movement, and interaction within the game environment. Now let's start writing our code. We'll begin almost the same way we did in the renderer file. First, we import the Turtle module, import Turtle. Then, we bring in all the constants we defined earlier by importing the constants file from constants import asterisk. These two lines set us up with everything we need to build the player, using Turtle's graphics engine and the predefined parameters from our constants file. Next, we create the general actor blueprint class, a shared base that our player will build on top of. So we write class actor with turtle.turtle inside parentheses, followed by a colon. This tells Python that our actor class inherits from the Turtle class, so we get all of Turtle's built-in functionality. Inside the class, we define the constructor, def double underscore init double underscore, with self inside parentheses, then a colon. This is the special method that runs when we create a new actor object. Then, we call the constructor of the parent class using super with empty parentheses, dot, double underscore init double underscore, with empty parentheses. That tells Python to run the turtle setup code first, so we start with everything turtle already knows how to do. After that, we apply two basic settings, self.speed with 0 inside parentheses. This disables animation delays, and self.penup with empty parentheses, so we can move the player without it drawing lines. That's our general actor blueprint. And now we're ready to build the actual player class on top of it. So we start by writing class player with actor inside parentheses, followed by a colon. This means our player class will inherit from the actor class, so it starts with the same setup. It is a turtle object with no animation and pen up so it won't draw when moving. Then we define the constructor, def double underscore init double underscore, with self, start underscore x, start underscore y, platforms, and walls inside parentheses, followed by a colon. We pass in 5 parameters here. Self is always the first parameter in a class method. It refers to the object we're creating. Start x and start y are the player's initial coordinates, so we know exactly where to place the character on screen. The platforms and walls are the same lists we created in the previous episode, and we'll store them inside the player object so they can be used later for things like collision detection and movement logic. Inside the constructor, we first call the parent class constructor, super with empty parentheses, dot, double underscore init double underscore, empty parentheses. This runs the basic actor setup. Then we set the player's appearance and position settings. Self.shape with the word turtle in quotes inside parentheses. This sets the player's shape to turtle's default turtle. We'll replace it with a custom shape later in the series. Self.shapesize with player shape size inside parentheses. This applies the proper scaling, based on the shape size constant we defined earlier. Self.setHeading with 90 inside parentheses. This method sets the direction the turtle is facing. In turtle graphics, 0 points to the right, 90 points straight up, 180 points left, and 270 points down. So by setting the heading to 90, our player will be facing upward. Next, we define the player's colors. Self.penColor with white in quotes inside parentheses, and self.fillColor with deep sky blue in quotes inside parentheses. This gives the player a bright, clean appearance on screen, but you can choose any color you like. If you're curious, just search Turtle Colors list on Google to explore all available options. Next, we define a new instance variable called self.keys, and we set it equal to a dictionary with 3 keys, right, left, and space, each one starting with the value false. So what's happening here? This dictionary acts like a virtual keyboard tracker for our player. It keeps track of whether each movement key is currently being pressed. But first, what exactly is a dictionary in Python? A dictionary is a built-in data type that stores data in key value pairs. You can think of it like a real dictionary, where each word is the key and the definition is the value. Dictionaries are written using curly braces, with each key followed by a colon and its value. In our case, the key is the name of the button, like right, and the value is either true or false, depending on whether that key is being held down. So if the player presses the right arrow key, we'll update the right value to true, and when they release it, we'll set it back to false. Same goes for left and space, which we'll use later for jumping. By checking these values inside our game loop, we'll know exactly which keys are being held down, and we can move the player accordingly. This approach is much more reliable than handling key presses one by one, because it lets us support multiple keys being pressed at once. For example, moving left and jumping at the same time. We'll wire this up to actual keyboard input a little later in the episode. Next, we set the player's starting position by writing self.goto with start underscore x and start underscore y inside parentheses. This moves the player to the exact coordinates we passed into the constructor, placing them right where they should spawn when the game starts. After that, we store two important lists inside the player object. Self.platforms equals platforms, and self.walls equals walls. These are the lists we'll pass in when creating the player object, and they come from the platforms and walls we defined in the previous episode. Each one contains the coordinates of the level's platforms and sidewalls. By saving them as attributes, we'll be able to check for collisions and interactions later on, like landing on platforms, bouncing off walls, or preventing the player from walking through solid objects. Then, we define a simple player attribute, self.can_jump equals true. This will help us control whether the player is allowed to jump. For example, we'll allow jumping if the player is on a platform, but disable it while they're in the air to prevent double jumping or floating. We'll use this flag inside the movement logic a bit later on. Next, we define two variables to track the player's movement speed, self.dx equals 0 and self.dy equals 0. These stand for delta x and delta y, which means change in x and change in y. In other words, how much the player moves horizontally and vertically each frame. At the start, both values are set to 0, since the player is standing still. By adjusting these values during the game, we can make the player accelerate, jump, or fall smoothly, just like in a real platformer. These values will constantly change during gameplay, and we'll use them inside the move method to update the player's position each frame. Now, we'll define the player's methods, and start with the methods for keyboard control. Each one of these will respond to a specific keyboard action and update the dictionary values we set earlier for right, left, and space. Let's go through them. We start with def go_right with self inside parentheses : This means the player has pressed the right arrow key. So we write self.keys, open square brackets, quote right quote, close square brackets, equals true. Then we define def go_left, which handles the left arrow key. We set self.keys, open square brackets, quote left quote, close square brackets, equals true. Next, we need methods for when the keys are released. Def stop_right means the player has released the right key. So we set self.keys, open square brackets, quote right quote, close square brackets, equals false. And for the left key, def stop_left, we write self.keys, open square brackets, quote left quote, close square brackets, equals false. We do the exact same thing for jumping. Def press_space is triggered when the player presses the jump key. So we set self.keys, open square brackets, quote space quote, close square brackets, equals true. And def release_space sets it back to false when the key is released. So all of these methods are directly tied to the keys dictionary we created earlier. They let us track which keys are currently being pressed, so the player can move, jump, or stop at exactly the right time. And when a value is set to false, that simply tells the game, hey, this key is no longer being pressed, so stop whatever action it was doing. Now that we've created the key control methods, we need to tell the program what actually happens when each key is pressed. So we define a new method called keyboard_input. This method checks which keys are currently being pressed and updates the player's movement speed accordingly. Let's walk through what it does. First, we define the method def keyboard_input with self inside parentheses, followed by a colon. Now, we start with an if statement. An if statement simply checks if a condition is true, and if it is, it runs the code inside the block. So we check if self.keys with right in quotes inside square brackets, colon. If that's true, it means the player is holding the right arrow key. Then, we check the current movement direction. If self.dx is less than 0 with a colon, that means the player was moving left, because dx being negative means movement is going to the left. Now, since the player is switching directions, we add acceleration multiplied by turn factor to self.dx. In code, this looks like self.dx plus equals acceleration times turn factor. This makes the switch feel more natural and responsive, instead of instantly flipping. Then, we check if the player is already moving right using else. If so, we simply add the acceleration to self.dx without multiplying by the turn factor. This means the player will keep speeding up, as long as the right key is being held. The left key works exactly the same, just in the opposite direction. So we check if self.keys with left in quotes inside square brackets, colon. If self.dx is greater than 0 with a colon, that means the player was moving to the right. So we subtract acceleration times turn factor from self.dx to create a smooth switch to the left. Otherwise, we just subtract acceleration normally to keep moving left. Next, we check if the space key is pressed. If self.keys with space in quotes inside square brackets and self.can_jump followed by a colon. If both conditions are true, we make the player jump by setting self.dy to the jump distance, and we set can jump to false, so the player can't jump again while in mid-air. This method will be called inside the game loop, so it runs continuously, checking which keys are active and updating the player's movement in real time. Now we define the move method. This method is what actually moves the player on screen, based on the speed values we've calculated earlier. We start by defining the method, def move with self inside parentheses, followed by a colon. The first thing we do inside the method is calculate the player's next position. We write next_x equals self.xcore with empty parentheses plus self.dx, and then next_y equals self.ycore with empty parentheses plus self.dy. The xcore and icore methods are built-in turtle functions. They return the current x and y's position of the turtle on screen. So here, we're taking the current position and adding the change in position based on the player's speed to figure out where the player will move next. Then we check if the speed is very small. Specifically, if the absolute value of dx is less than 0.1. If it is, we set self.dx to 0. This helps us avoid tiny movement values that could cause jittering or unnecessary updates. This check is especially important because later on we'll add friction, and that could leave behind small leftover values we want to cancel out. Next, we use the goto method to actually move the player, self.goto, with next x and next y inside parentheses. This updates the player's position on screen based on the movement we just calculated. Finally, we set a maximum limit on how fast the player can go. We check if self.dx is greater than max speed, we set it to max speed. Else if dx is less than negative max speed, we set it to negative max speed. This keeps the movement under control, so the player doesn't accelerate forever. And that's our move method. It keeps everything smooth, fast, and responsive by updating the player's position in every frame. Now we define the method that puts all the pieces together. It's called update. Technically, we don't really need this method. We could just call each individual method, like keyboard input and move, directly inside the game loop. But writing an update method makes our code more organized and easier to manage. We define it like this: def update with self inside parentheses followed by a colon. Inside this method, we start by calling self.keyboard_input, which checks for key presses and updates the player's speed. Then we call self.move, which actually moves the player based on the speed we just updated. Later on, we'll also add things like gravity, friction, jumping logic, collision detection, and animation. And this update method is where we'll tie all those things together. So think of update as the master method. It handles the player's behavior for the current frame and makes sure everything runs in the correct order. Now let's switch back to our main.py file and create the actual player object. We'll also set up the keyboard controls, so the game knows what to do when the player presses a key. First, we need to import the player class. Right below the import from renderer line, we add From Actors, import Player. Now scroll down below the Init screen function, and let's define a new function for keyboard bindings. We write defbind_controls with screen and player inside parentheses, followed by a colon. This function will handle all the keyboard setup. Inside the function, we start with screen.listen with empty parentheses. This tells the turtle screen to start listening for keyboard input, so it can respond when keys are pressed or released. Then, we bind specific keys to the player's movement methods. We write screen.onKeyPress with player.go_right and right in quotes inside parentheses. This means when the player presses the right arrow key, call the goRight method from the player class. Next, screen.onKeyRelease with player.stop_right and right in quotes inside parentheses. This means when the right arrow key is released, call the stop right method to stop movement in that direction. We do the same for the left arrow key. Screen.onKeyPress with player.go_left and left in quotes inside parentheses, and screen.onKeyRelease with player.stop_left and left in quotes inside parentheses. Finally, we set up the jump key, which in our game is the spacebar. We write screen.onKeyPress with player.press_space and space in quotes inside parentheses, and screen.onKeyRelease with player.release_space and space in quotes inside parentheses. So this function connects the keyboard keys to the player's input system we built earlier. Later in the code, we'll just call this function with the screen and the player, and everything will be ready for real-time input. Now scroll down to the game loop function. We need to update this function to support the player's movement and controls. Even though we haven't created the player object yet, we'll prepare the function to work with it. First, we update the function definition. Right after the parameters for screen, walls, and platforms, we add a new parameter called player. So it becomes defGame_loop with screen, walls, platforms, and player inside parentheses, followed by a colon. Next, inside the function, just above the screen.update line, we write player.update with empty parentheses. This will run all the player logic, including keyboard input, physics, and movement. Finally, scroll down to the line with screen.onTimer. Here, we also need to pass the player to the recursive call, so it becomes screen.onTimer with a lambda that calls game loop, passing screen, walls, platforms, and player. By doing this, we make sure that the player gets updated on every frame, and the game loop keeps running smoothly at 60 frames per second. Now we scroll down to the main function, and right below where we create the platforms, we create our player object. We write player equals player with 0, player_start_y, platforms and walls inside parentheses. We're passing in 4 arguments. 0 is the X position, so the player appears right at the center of the screen. Player start Y is the player's starting height, which we calculated earlier in the constants file. Then we pass in the platforms and walls lists, so the player can later use them for things like collision detection. Next, we call the bind controls function and pass it the screen and player. This enables all the keyboard inputs we set up earlier, so the player can move and jump in the game. Finally, we pass the player object to the game loop call, so it updates in every frame as the game runs. That's it. Let's run the game and see what we have. You should now see a game window with walls and platforms, just like we had so far, but with the addition of the player starting right on top of the floor, shaped as a turtle and facing up. You can now control it using the arrow keys. Notice that the player accelerates as you keep holding left or right, up to the max speed. They can also change directions. Right now, they won't stop on their own because we haven't added friction yet. And if you press space, the player starts moving upward. Since gravity isn't implemented yet, they'll just keep floating upwards forever. But we'll fix all of that in the next episodes. Before we wrap up, let's take a quick look at what we've built. In this episode, we created the player character and brought them to life. We set up keyboard controls using a simple dictionary system and connected movement methods to real-time input. We also handled acceleration, allowed for smooth direction changes, and made the player jump with the space key. Finally, we plugged everything into the game loop, so the player now updates on every frame. In the next episode, we'll take things to the next level by adding physics and collision detection. You'll learn how to simulate gravity, land on platforms, and prevent the player from falling through the floor. It's where the world starts to feel real, so don't miss it. If you found this helpful, a like and subscribe would really help support the channel. And make sure you don't miss what's coming next. I'm the Wannabe Coder. Thanks for watching, and I'll see you in the next episode.